Hello, and welcome to today's PSU Transportation Seminar. My name is Jason, and I will be introducing and moderating today's seminar. Our PSU Transportation Seminars have been a tradition since the year 2000. These seminars are once again being held live on Portland State University's urban campus, located on the ancestral homelands of the Multnomah, Cathlamet, Clackamas, Tumwater, and Watlala bands of the Chinook, Tualatin, Kapuya, and many other indigenous nations of the Columbia River. It is important to acknowledge that we are here because of the sacrifices forced on the indigenous ancestors of this place, to remember these communities and to honor their legacy, lives, and descendants. Today, we are pleased to have Tanmoy Bhowmik, hope I pronounced that correctly again, presenting on the driving future intersection of emerging transportation technologies and energy consumption. Dr. Bhowmik joined the Department of Civil and Environmental Engineering at Portland State as an assistant professor this fall. Prior to that, he worked as a postdoctoral associate and graduate faculty scholar at the University of Central Florida. His research primarily consists on the formulation and development of data-centric statistical and econometric models and applying them to different transportation sectors, including transportation planning, safety, and energy, to understand the underlying behavioral patterns and decision processes. This is the final seminar of the fall term. More information about winter and spring term seminars will be announced soon. As an overview of today's seminar, you can expect our speaker to present for about 40 minutes, followed by a Q&A session. We will be receiving questions to the Q&A feature on your control panel, and we'll ask them at the end of the presentation. If we run out of time for all of your questions, we will give our speaker the opportunity to email written responses for any questions left unanswered. We have enabled closed captioning, but you must click on the CC feature on your control panel to view them. We will be recording today's webinar. It will be available on our website later today, along with the presentation slides. If you are tracking professional development hours, this webinar is eligible for 1 hour of continuing education credit. With that, I will hand it over to Tanmoy to present.
Thank you, Jason, for the nice introduction, and thank you for giving me the opportunity to present one of my work to you. I think Jason has covered everything about my introduction. I do not want to add anything new. Just one thing, like my work mainly focused on statistical and econometric models, especially to develop some models when some simplistic models cannot be proposed. Like one example I could be given is whenever we do choice analysis, multinomial logic model is one of the simplest models that researchers usually adopt. But if we have multiple choice, let's say I want to develop a destination choice model when I have 100 or 1,000 of destinations to choose from, developing a multinomial logic model is not feasible. That's where my work blends in. I want to come up with the econometric models so the model could be simple, efficient, and can have the same infrastructure as the logic models. So my work mainly focuses on those kind of econometrics models. And in today's presentation, I want to talk about something about the ever-evolving world of transportation and how the transportation is connected to other sectors. So, like, if transportation is going through a rapid transformation day by day. For example, like every day we are seeing new innovation and new advancement in the transportation sectors that are reshaping how we usually move from one place to another. Like electric scooters buzzing around the streets, from self-driving cars navigating our roads. These are some of the examples how transportation is going through rapid transformation every day. Now the real question is it a solo network? So is the transportation network is very simplistic? And the answer is no. There are lots of components that is integrated on the overall network. And one change in one component have an impact on other sectors. For example, when Uber hit the scene, it completely reshaped our understanding on how shared rides are being considered. it has an overwhelming effect on the taxi ridership. Now think about when self-driving car or autonomous vehicle comes into the picture, what will happen to the Uber riderships? So this is an example that how a new innovation or new technology can have an impact on the past studies, on the past research, or on past sectors. In today's presentation, I want to highlight one such impact: the emerging technologies of electric vehicles, connected autonomous vehicles, and how does it connect it to the energy consumptions. So, as you all know, EV shares or electric vehicles are increasing day by day all around the world. And this nation, United States, also no exceptions. To give you an idea, in 2020, the electric vehicle share was around 2.5%. Fast forward to 2022, the share becomes 5.6, more than double. By the mid of 2023, it is now 7.6. So that means almost 1 million of new electric vehicles are going around the road in every year in the United States. This trend shows that people are getting more and more inclined to electric vehicles because of the reduced harmful impact on the environment, and as well as it saves money to them because they do not have to pay for gas. But there are also some barriers in adopting those technologies. One of the most common barriers is the charging inavailability. My focus is not who are not, my research, this research doesn't focus on who is not adopting electric vehicle. This research actually focused on who is adopting electric vehicle. And when I do the analysis, something interesting, we got it. About all the electric vehicle owners in the United States, 80% of them prefer charging a station installed in their home. Even though there are available charging station around their location, they want it in their home. The question is why? Because of two significant factors. Number one, it's cheaper. They can charge their vehicles at lower residential electricity rate compared to the charging station. But the most significant factor is convenience and comfort. Think about something. If I have a charging station in my home, I can give my vehicle overnight for charging, and every morning when I woke up, I have a fully charged vehicle. And because of this comfortness, people prefer installing a charging station in their home. Now comes my point. Because of that charging station installation in the home, it has an impact on the residential electricity consumptions. Whatever electricity is consumed by the building before, that consumption right now is increasing because of those charging. And with more EV vehicle plugging in the future, the demand will substantially rise. Some researchers has found out, like by the end of 2040, the electricity consumption rate might increase by 200%. It's 200%. So that's a very, very big number. And these residential buildings are finally connected to the energy grid. So if the electricity consumptions increase by 200%, the real question is whether the electricity grid might go out of capacity. And if so, at what point? So we need to be prepared. And the base system to be prepared is we need to have a base system, base model or base simulator where we can change the ratio of electric vehicle and see if we change the electric vehicle share to 5% to 10%, 10% to 20, 20 to 50, what will be the resulting residential electricity consumptions and what will be the resulting impact on the overall energy grid. And only then we'll be able to find out if and what point the electricity grid has to work out like never before. And that is the main focus of this study. So now looking at literature, there are a lot of research has been going on to understand the energy prediction models. From the literature, I found out 4 distinct data sources. Starting with, the first one is utility companies like the PG&E, Pacific Gas and Electricity Company. Is one of the largest company in California that provides data to the researcher for analysis. It provides information on residential energy uses. It provides information on household characteristics. And the best thing about this data is it provides every individual specific household level information. So data is very comprehensive in nature. But there is some issue on those data. First, there are obviously some privacy concerns associated with some data. And that is why some important information are always missing from those data sources. They deliberately do so to avoid the privacy concern. Second, collecting this data or getting this data is expensive. Third, they only provide a subset of sample. That sample doesn't represent the overall population of the nation. And if that doesn't represent the population of the nation, that means any analysis or any model or any simulator being developed considering this data does not represent the nation. So cannot be applied nationwide. Then the second one, smart meters data. There are some companies like Itron, Honeywell, or Siemens that install smart meters on the building. These meters capture real-time energy pattern, real-time energy uses. So let's say at 11:30 a.m. in the morning, for some reason the electricity consumption was peaked. By researching in the smart meters data, we'll able to know why the peak has been observed in such time period. But the challenges still associated is the same as the utility companies. First, because of the high installation cost, very few number of households have installed smart meters in their house. And that is why the number of sample is very limited, and the same issue still exists. It doesn't represent the overall population of the nation. Then the third one, researchers conduct a survey, and that is the most comprehensive analysis researchers can do. They can collect information on housing characteristics, they can collect information on employment characteristics, they can collect information on energy uses, and most importantly, they can collect information on psychological factors like, are you willing to buy electric vehicle, and are you willing to install a charging station? So it can correct a very comprehensive nature of the trend of electric vehicle uses and the resulting impact on the energy. But the issue with such data sources is, first, it's a time-consuming thing. Starting from the preparing phase to the administration phase, conducting a survey is a very time-consuming thing. Second, the analysis solely depend or purely depend on the participation rate. If you get enough sample from the survey, you are lucky and you would be able to develop a model. But if you do not get enough sample, that means the same issue still exists. It might not represent the population. Third, there are always selection bias. To make the survey representative, you need to have participation from people all around the world, including different age group, including different gender, different employment characteristics, different income, and so on. That is hard to do. I'm not saying impossible, but sometimes that is hard to do through a survey, though this is the most proficient method to gather comprehensive information. Then the last one. This is also a survey data, but this is conducted by some national agencies, and those information are representative of the nations. Those information are collected at a state level, at a regional level, or at a national level. Some information is like the residential energy consumption data. This survey is conducted by Energy Information Administration. They conduct this survey in every 4 years, starting from 1978. They collect information for different households and different variables. Like I'm showing in this slide, they collect information for around 5,500 households. That represents around 118 million households in the United States. And they provide information for 4 different energy sources: electricity, natural gas, fuel oil, and propane. And at the same time, they provide information on housing characteristics, how many number of bedrooms are there, what are the different appliances uses, when the house was built. Then climatic variables like heating or cooling days. Heating and cooling days mainly represents the hot and cold region. Like if the heating days is higher, that means that house is in a colder region, and that's why the heating days was higher. If the cooling days was higher, that means the house is in a summer region. That's why the cooling days was higher. This data is very good and it represents the nation. But the issue is it lacks two important information. First, the focus of my study, I want to see is having an electric vehicle and because of that charging, how much does that impact the energy consumptions? But the RECS data that we have doesn't have information on the household vehicle ownership and doesn't have information on the electric vehicles. Second, it doesn't have information on the employment characteristics. COVID-19 has altered our travel behavior and introduced a new trend, the remote work arrangement. With more people staying at home, with more time spending at home, the residential electricity consumption will increase. That information I need to include in my model, but it's not there in the RECS data. So these two information, though very important, are not present. Now, this information is present in another data source. It's another survey, National Household Travel Survey data, that is conducted by Federal Highway Administrations in every 5 to 7 years, collect information on around 130,000 households that represent the same 118 million houses in the nation. The information was present in NSTS, but the issue is NSTS data doesn't provide information on the energy uses. Now, there's the problem. The research that I want to do is how much the electric vehicle, having an electric vehicle in a house, impact the energy uses. I have those information, but in two different data sources. I need to, if somehow I can connect these two systems, my problem is solved. But to merge the data or connect two data, we need to have a common identifier. We don't have any. In these two data sources, we don't have any. There is no way I can say that household one in RECS and household one in NSTS are the same. We cannot, because there are no common identifier. So that's one of the methodological contribution of my work. What if we combine these two data sources behaviorally? To give an example, let's say today I make a decision. I want to combine my information with all of you. The idea is if my other characteristics, like I am wearing a glass, I am 5'10", I am a male. If I found another person who is wearing a glass, who is 5'10" and a male, if my characteristics are matching with someone, maybe at some point my decision will be matched with that person. That was the idea. So following on that idea, the first thing to understand, what are the common variables present in these two data sources? And these 7 are the common variables that I found. Both data sources provide information on the size of the household. That means how many members, on the number of adults, the household race, the homeowner status, whether the house owned by the person or it's a rent, the household location, at what location the household is located, household region, and household division. These 7 information are common, present in both. Think about something. Now, my first assumption is let's want to merge these two data sources based on all these 7 characteristics. I didn't find any match at all. If I want to match my characteristic with the person here, and if the more restriction I add, the lesser matches I will get. The more flexibility I add, let's say I just want to match my record with someone as my height. I might find 5 to 7% here. But if I want to have matched someone with my height and wearing a glass, I might find 4. If I add one more restriction, I might find 1. If I add one more restriction, I might not find any. So even if I want, I cannot match with all 7. The example I showed, the same example. The lesser restriction I have, now I want to match based on 5. I found 3 matches. This is the example I'm showing. I want to match based on 3. I found more matches. I want to match based on 1. I might a significant number of matches. So that's the first question in my fusion method. What variables I should use to match the two sources? we need to answer that one. I'll come to that eventually. The second point is, let's say somehow I found out that variable 1 and 3 are the best variable to match these two systems. How many records do we match? Like for this one household, I found around 10 to 12 matches. In any modeling technique, if you have high number of, I'm talking from modeling perspective, we shouldn't run a model with very high number of observations because that will induce a bias. First of all, if you run a model with 10,000 records, and if you run a model with 100,000 records, both model will interface differently, because with 100,000 observation, any variable you will try, all variables will come significant. No matter the variable has an effect or not, it will come significant because the number of observation is very large. There are research that shows that the optimal number, there is no optimal number actually, but the usual or optimal number should be around 7,000 to 10,000 records. It is standard. It is, I'm sorry, I shouldn't use standard. It is shows that this number is in the ballpark. So if you can have a model with 20,000, you can have a model with 30,000. But if you, as I mentioned, if you develop a model with 100,000, 200,000, your model will have some sort of biasness, because all variables, any variables you will try, you'll have everything significant. So then the second point, your complexity will increase. Your model run times will increase substantially. So after I find some matches, I have to come up with optimal number of matches. I cannot use all 15, because if in my RECS data, I have 5,000 households, and if I found for every household, I found 30 matches, that means I have 150,000 records right now, or more, if I'm not wrong. So I need to come up with the optimal number of match. That's the second question I need to answer. Now moving on the last one. Let's say I find 5. From somehow I say, okay, 5 number of matches is optimal. Please remember, I have 15 initially. Out of this 15, I select only 5 by random process. Now I run the model. You again run the model with the same random process. The 5 that I select and the 5 that you select might be different. And the model that I have and the model you have, that might be different as well. So that means if I select randomly every time, my model might not be stable. It might produce different result. So I need to make sure whatever I am doing, it produces stable result. That's I need to make sure. I need to make sure the randomness doesn't have any impact on the model. So that's the third question. So in total, in the future, I have 3 questions. 1, which variable I should use? 2, how many records I should take? And 3, is the result stable or not? Is the randomness has an impact on the result? Then last, please remember, let's say I use 5. Somehow I find out 5, and somehow I found out my model is stable. Then the last step, let's say I have 100 households in RECS. I select 5 from NSTS. Now I have 500 households. These 500 observation still represents on those 100 households. So I have to introduce a weight to make sure the 500 observation I have is actually represent the initial 100 households from RECS. And the simplistic way to do it is introduce a weight and equal weight. If I match 5 records, the weight would be 1/5. If I match 10 records, the weight will be 1/10. Then I did some modification. I said, what if I can improve the weight? Please remember, I have 7 variables. In my analysis, I found the first 3 is the best to match these 2 data sources. I still have 4 remains. I can use this 4 as a variable in the weight function. The idea is, after matching the 2 data sources, I have 5 records. For each household, I have 5. Out of these 5, if any of these things matches in any of the records, that record will have higher weight compared to the other 4 records. That was the idea. So this is the overall fusion method. And this is the data. I didn't show any data description or anything. If you have any question, just email me and I will share that paper with you. So as a dependent variable, I focus on two types of energy uses, electricity and natural gas, because those two comprises of around 90% of the overall energy consumptions. And as a variable, I use appliances like what are the electricity consumed, what are the cooking device has been used in that house, what are the air computers has been used in this house, then climatic variables like heating and cooling days, then housing characteristics like when the house was built, how many number of bedrooms, then locations. Finally, I include information from the NSTS. This is the new thing. In any energy prediction models, this was missing. This was the variables that I added through my fusion analysis. Now, let's answer those questions. So, how do I select which variable is give me better result? What did I do? I develop a model focusing only on the RECS data, no fusion. I developed a model using the fusion, checking different variable combination. I fused these two data sources based on household size. I fused these data sources based on household size and household race. I check different number of combinations. The combination that gives me highest improvement compared to the unfused model is my optimal choice for that variable. I didn't present everything, but in my analysis, I found if the two data sources are merged based on the same household division and same household area, urban and rural, those analyses produce the highest improvement. So I select this and proceed to the next step. The next step is, let's say I merge these two systems based on household division and household area. How many records do we take? You will see the more record we take, the improvement is higher. But at the same time, the green circle shows the complexity, the computational runtime in minutes. The more records I add, the more records I fuse, the computational runtime is also increasing substantially. So I have to come up with an optimal solution, and in here I select 10 to be optimal because with the highest improvement I got is in 20. So if I take 20 records from NSTS and fuse it to the RECS data, it gives me the highest improvement. But it also associated with one of the highest computational runtime. But when I compare from 10 to 20, the improvement is around 6%, but the computational runtime increased by around 50%. That means 10 is my optimal choice. I do not need to go to 20. 10 is my optimal choice because it gives me relatively better improvement. At the same time, it is less time to run the model. So I take 10 records. So in summary, till now, I fused the two data sources based on same household division and same region, and I take 10 matching records. At least 10, sorry, at max 10. If I found less, I'll take that. But if I found higher, I'll take 10 randomly. Then my last question, are my models stable? And to check that, what did I do? I run my model 20 different times. Every time I take 10 randomly based on the similar characteristics. The idea was when I have 10 different models, that means for each variable, I have 20 different models. For each variable, I have 20 different coefficients. If the coefficients are significantly varies across the sample, that means the randomness has an impact and the fusion analysis is not stable. But if the coefficient doesn't change over sample to sample, that means the fusion is not affected by that randomness. I plot it as a box plot here. If any of the numbers goes past the critical T state, which is 1.65 in 90% confidence level, that means that for that variable, the parameters are significantly varies over the samples. See, the highest number I have is 0.25. I have to go past 1.64 to hypothetically saying that the parameters are varying over the samples. Nothing varies. So that means that 20 different models I run, I found similar coefficients. So the result I have is a stable model, and the fusion I got is a stable analysis. Then I did everything. Now I need to check, am I really improving the model or not? And the best thing to do is checking the BIC. The first one is no fusion. The RECS data that I have, I run it. I don't have electric vehicle information. I don't have employment information. I have whatever I have in the RECS data. That's it. The second one is I fuse the data sources, but I introduce equal weight. The third one, I fuse the data sources and I express the weight as a function of other matching variables. If you look at the BIC, it shows, first of all, the fused model always providing a better BIC results. So that means your model performance is getting improved because of the fusion. Second, compared to the fused model, the model with probabilistic weight have a better results. The two tables I shows, one for natural gas, one for electricity, and the result is consistent. Whenever I have a fused system, the model is improved. Whenever I introduce a probabilistic weight system, the model is further improved. And this is the result. Because of the lack of time, I'll not go through the results one by one. The results are in line on previous research, like, for instance, like if you see like the construction year of the house, it shows the base here is before 1980. So it shows newer households have higher electricity consumptions. Yes, newer households have higher electricity consumptions compared to the previous households. It might shows like our more use of computers, desktops, portable ACs, and so on. Same thing with appliances. More appliances we use, more electricity will be consumed. So these all results are actually aligned with previous research. So I'll not go over this. I'll go over this part because this table is the additional thing that I added to the energy prediction model. The highlighted one, just see. If I have higher proportion of electric vehicles in the house, the electricity consumptions will go up. It makes sense because I have electric vehicle. I want to charge my electric vehicle. I have a charging station, so electricity will go up. Second, if the number of people work from home goes up, both electricity and natural gas consumption will go up. It also makes sense. People are spending more time in their homes, so they are using more appliances than before, so the electricity goes up. All the information presented here are the addition to the energy prediction model that has been going on. And all the information presented here are the connections to the transportation, from the transportation sector to the energy sectors. And this is the weight. To give you an idea, the first one is household member differences. So I have household size in RECS, I have household size in NSTS. Both these data source, if the household member differences are 0, that means both data have same household size. It shows if the differences goes high, that records consume lower weight. It makes sense. If the differences are in the lower side, that means those two households are more matched, so the weight is higher. If the differences goes high enough, that means those two are not matched based on household members, so the weight is lower. So that is an addition. Instead of using an equal weight system, we can use a probabilistic weight system. Now, I did my models, I did my analysis. I need to check with the validation, and I did something else. When I submit the paper, I got a reply that maybe your model is doing good on your sample size. What if I select different? And that's why I extend my analysis considering different sample sizes. And the result is consistent. Every time, the first one, it shows the comparison from fused, unfused to fused model with equal weight. The second one is the fused to fused, but equal to probabilistic weight. Every time, first of all, fused model has an improvement compared to the unfused model. Second, The probabilistic weight method has a further improvement compared to the deterministic weight fused model. So the result is consistent, and for every sample size, for estimation and validation, both sample, the result is consistent. So that proves the energy prediction models is improved through the fusion. Then I predict on the regional level. The left side is the overall predictions. Please remember the number is in trillion British thermal unit. So even though the graph shows similar, even the difference is 1 trillion BTU is more than enough. That's why I present the error. And look at the result. This one is just a model with RECS data. This one is the model focusing on both RECS and NHTS fusion. This one focusing on the fusion plus the probabilistic weight. The error is much more lower compared to in the probabilistic weight method. Now someone can ask me that you are still off by 104 trillion BTU. Yes, I am, but I am improving whatever is going on in the traditional system. I improve by 135 trillion BTU. And I did my model based on 2015. I predict on 2020. So my model prediction is also improved. And then last, I did all of these things to understand what is the impact of EV. This is what's being projected in the RECS data, the energy consumptions. Now see, because of my model, I show if the electric vehicle increase by 6 or 12%, what is the resulting outcome? The electricity consumptions will increase around 15%. This 6% is the overall increase. That means if the current rate is 5%, the 6% increase from the current rate means the share will become 5.3. So it's a very small increase. But for this small increase, the electricity consumption increased by 15%. So the research, the result I found is also aligns with what's being found in one of the study that by the end of 2040, if electric vehicle share goes up to that mark that being expected, like 50 to 60%, the energy will increase by 200 to 300%. And this is the impact of work from home and the combination of EV and work from home. So in summary, I propose a novel fusion model, novel fusion algorithm. The best thing is it can be applied to any field wherever it is possible to connect the two data. It is not possible to connect the two data based on, because there is no common identifier, it is not possible to connect it. This fusion algorithm can be applied there. Like one example I could give is when we want to do demand analysis in transportation, we focus on survey related data. So my fusion algorithm, the location-based surveys or GPS data can be connected to the survey data and the spatio-temporal coverage can be improved. Another implication is, which I also did, is improving the evacuation model. People rely on Twitter data or social media data because it's produced real-time information. But the problem is not everybody uses Twitter. People from different age group do not use Twitter in the same manner. So it is not, there is always a point that it is not a sample representative model. If using this fusion algorithm, I merge the Twitter data with the National Household Travel Survey data and make it a representative sample. So in summary, in the work, I propose a novel fusion algorithm, I improve the energy prediction models, and I propose a policy scenarios for different EV share. Now, the work is also not without limitation. Again, I distributed this work in 3 phases. My idea is my final outcome is to develop a simulator so I can change the electric vehicle ratio to see in a city, changing the ratio, how much electricity will be changed or increased and what will be the impact on the energy grid. In my first phase, I need to make sure that whatever fusion I am proposing is working good. So this is the first phase of the study. The full purpose of the study to show that the fusion that I propose is working well and effectively. So, second limitation of the study is I focused on 2015 RECS data and 2017 NSTS data. In 2017 NSTS data, the percentage of EV and work from home is very, very, very low. If from a modeling perspective, we shouldn't use that as a variable in the model. But because till now, the 2022 NSTS data is not publicly available, though all of us are eagerly waiting for that data to be available, I do not have anything else to use. So that's why, even though I have very less number of EV shares, I use that as a variable in the model. Third, the idea is on the overall energy grid. And to better understand, I need to develop an integrated system focusing on both residential and commercial energy demand. Because one example is, if you spend more time in home, that means your residential demand is going up. But at the same time, your commercial demand will go down. So they are cross-cutting each other. So it will be efficient if you have an integrated simulator that focus on both residential and commercial demand. That's my last phase of the work. And last, I need to develop a simulator from the starting phase, focusing on in a city, who will be willing to buy the EV, who will be willing to install a charging stations, and then use this fusion method and find out what is the resulting energy, residential and commercial energy demand. And that will give me a full picture of what will go on in, let's say, 10 years into the future. So with that, yeah, I came to the end of my presentations. So I share my email address here with the slide. So if you have any questions, I'll be very glad to answer that. And thank you.
Thank you, Tanmoy. For those viewing the webinar, please feel free to submit your questions using the Q&A feature in the control panel on the bottom of your Zoom window. We'll go ahead and start with a question from anyone that's in the room.
Yes.
First, a comment. The NHGS data was just released in the past week.
Oh,
in case you missed that. So start on, I don't know about obviously the other data set. So
okay.
those of us who use those data are pretty excited that it's now available. I guess my question for you would be sort of other ways, focusing just on the question of predicting future residential electricity demand, given the driving forces, particularly of EVs, but you've added in work from home as well, which is another factor, maybe more complicated. What would be like, how are other people forecasting this? Like, what are the alternative methods of trying to forecast that change in demand?
One of the most traditional method to forecast is using a time series analysis. Like from the literature, I found what they did was they focused on the time series analysis, and then they added the two new significant things. They do not add the number of working from home, because working from home doesn't have that much impact. They only add the electric vehicle share. So what they did was, because of the electric vehicle having an electric vehicle on the home, how much the electricity change in that particular hour or over the day, they have this prediction fixed, and then in the model they use the previous time series analysis to use the energy predictions and add the corresponding EV share percentage. I don't know if I able to, convey that message. The problem is, I'm not saying that is wrong. Mm-hmm. The problem is, when you predict two things differently and add it and having a demand, you are missing the confounding effect. What I'm trying to say is, let's say I develop a model focusing on two variables. I develop a model focusing on two other variables. I add these two systems, and I developed a model focusing on four variables. These two systems are different, because when I developed a model focusing on four variables all together, I am avoiding the confounding effect. So, but when you have a model focusing on two variables, I developed a model focusing on four variables. These two systems are different, because when I developed a model focusing on four variables all together, I am avoiding the confounding effect. So, but when you have a model focusing on two variables, I developed a model focusing on four variables. These two systems are different, because when I developed a model focusing on four variables all together, I am avoiding the confounding effect. So, but Obviously, the time series method is more simplistic to adopt compared to having this system, because like any modeling techniques, no one can be sure that how much that will hold. Like the prediction might change in next year because some additional things comes into the picture. But with the time series, because there is a historical analysis, it is the simplistic method to do so. So to answer your questions, I found people are using that. So they conduct surveys, they understand who are willing to buy the EV, who are willing to install charging station, they develop a model, what will be the resulting predictions. They have the historical analysis in last 10 years, they add these two systems and they say that might be the outcome. That's how the studies that I mentioned, I forgot the name of the author, that's how they shows like the electricity might increase up to 200% by the end of 2040. That's how they mentioned. They did a survey. They said how much the EV will come into the picture. They analyze this literature and see because of EV how many electricity is consumed in a day, and they add these two systems.
Thanks.
Yes. So kind of in a similar vein to Jennifer's, Dr. Leo's question, since there are certainly you in the fusion process, of course, you did a bunch all your analysis. I believe it's a vigorous process. But how is your results compared to, say, results utilize utility data sources, utilize just complete survey data? I believe such data set must exist, even though it could be maybe a smaller sample that include the household energy consumption, EV ownership, and housing, or household characteristics, and so on. But one thing, at least maybe one example, for example, how your results compare to results from those model, those analysis is, at least I feel the year built coefficient, as you described, is still a bit counterintuitive.
Yep.
Since you already controlled for the size of the home, you're already controlled for appliance, right? So AC and all, and so on, so on and so forth. It's a bit counterintuitive why older home actually consumes fewer, even if you're already controlled for pretty much all the confounding factors we can think of.
You were right. I didn't check. But the issue is, like, as I mentioned, with the utility company data, I cannot check on a nationwide. I might be able to check, like, with the utility company data, I might be able to check on the state of California, like the example I say. I didn't check that. That's a nice suggestions. Coming to the variables, when I was developing my initial models, I didn't use the construction period because it also shows me, it also tells me like maybe there are some kind of correlation that I was missing. So I check the correlation because I am actually what I am controlling for appliances. I am controlling for a number of bedrooms. So the construction period, according to me, should come negative. But I found those variables I actually tried based on earlier literature. But in the literature, they also, after controlling for appliances, they also found that the construction period compared to the previous year, newer households have high electricity consumptions. One possible reason is for this one, like appliances uses are only controlling for is how what are the frequency of appliance use. But what I didn't control for is the number of populations. Maybe in the previous house, the number of population is lower. So what I'm trying to say is the appliances use that I use in the model, it says in a day, how many times I use the computers. Think about something. But maybe in previous times, there are 5 different people that all use. So how they compute the appliance use is there are 5 different people. They just took out the maximum frequency of the computer used. Now, in previous year, maybe there are only 2 people in the house. So the combined appliances use may be only 2 times or 0. In the new years, there are 5 different households, 5 different persons, but the appliances use maybe 5 times. So what I'm trying to say is the concerns was valid if the appliances uses was generated based on the combined frequency use of all the peoples, not only on the maximum. That's what I was thinking, and that's why. But initially, I didn't try the construction period. But all the literature I found, because energy modeling is something I was new to also. So all the literature I found, any energy-related variables that I use, I focused on the earlier literatures. So they use the appliances uses, and they use the construction period. So to give you an answer, I think if the appliance uses represents the total number of users, then might be the construction period might not come significant, but it only use the average frequency or the maximum frequency the people are using on a day. Maybe that's why the confounding effect is not controlling for that variable and the construction period is coming. Also, the number of housing units, I didn't take account for that one. Maybe that has an impact. Before 1980, the number of housing units might be 20 or 30% less. But the resulting electricity consumption is the total electricity consumptions compared to that region. So because I didn't take account for any exposure informations, that's why. So if instead of modeling total energy consumptions, if I model energy consumptions per household, then maybe the construction period will not have a significant impact. If that answers your questions. But when I was developing the model, yes, that was the concept. So I checked the correlation also. I didn't find any correlations between these variables, though they seem correlated to each other. So, yeah. Yep.
Well, I guess I also wonder, well, now I'm a little confused about the unit of analysis, the housing units, but I also wonder if there's only a set list of appliances from the survey, right? So I wonder if newer houses are more likely to have types of appliances that aren't, or other electricity using devices that are not accounted for in the survey. But actually, there was a different result on the transportation side. You had total number of vehicles and then the share of the vehicles that are electric. And both of those were positive for electricity consumption. And I'm trying to figure out why the total number of vehicles would be more electricity. Because were you also controlling for income?
Yes.
Okay.
But I control for the income only for the high income. Yes, I also control for the income. But I didn't control for the number of drivers or number of workers. But I'm
just trying to think, because if you have all gasoline cars, that has nothing to do with electricity in your house, right? So if you had 4 gasoline cars and 0 electric cars versus a house with 2 gasoline cars and no electric cars, there's more electricity use in one with 4 versus 2. And so there has to be something else that's representing, right?
Yep, that's true.
Something else going on, or
no, I need to check because the result slide has been prepared one of my students, because in the initial analysis, you were right, in the initial analysis, I did not include the electric vehicle share. I only include the total vehicle because to just represent the electric vehicles. But the moment I have information on the electric vehicles, I might have removed the total number of vehicles from the results. So the total number of vehicles, I don't know if it's still there. The total number in the new paper, the total number of vehicles is not there anymore. So when I was first doing the analysis, I didn't find the electric vehicle share as significant because of some other variables. So then I reshaped the model And so that time I used total number of vehicles because electric vehicle is not coming significant. I use the total number of vehicles to serve as a proxy for the electric vehicle share. But the moment I have electric vehicle as a significant variable, I remove the total number of vehicles. So
Well,
but
maybe also with the new NHTS, you'll have.
I have more shares.
households
Yes,
with EVs
yes,
and-
yes,
And improve. them.
yes. But the total number of vehicles is not there. That I can assure you. So
Is there a question online or should I have a question?
I think this answers your question.
Go ahead, John, and then.
Okay.
Sarah, one on.
So the scale is still at, nationwide, but you were able to kind of get it by more regional.
Yep.
How do you see downscaling this? I mean, like, it's one thing to say like, okay, what is our energy consumption at, but certainly like even at the west, it's a very large,
Yes.
scale. And, we had a project a couple of years ago that we were trying to map BMT to the household in looking at potential for EV adoption at different economic scales. When we were trying to fuse those two data sources, which was difficult, and impute BMT to certain block groups. And so this is very interesting, that we have done a better job in doing that. But that was at the Portland metro region, kind of really looking at what would it do. And then, as you can imagine, utilities are very interested in this as how they manage demand and what will the demand be in the future. How do you think of your scale as you try to downscale, and how do you do that?
In this analysis, we can go to the downscale up to state level. There is something called metropolitan statistical area. We can also predict up to the metropolitan statistical area. That's the most disaggregate level informations these two data sources have. In a city level, using this analysis couldn't be done, but because those special units are not there, I only present the region level model here because of lack of time. But in my paper, I downscale to state level analysis also. I didn't present it here because the results are consistent. My model is improved. In the disaggregate level, I can go up to the metropolitan statistical area. If you want to go up to the Portland metropolitan area, one thing we can do is using these two data sources, it might be tough, the one I showed, because there are no spatial level information that can tells me these households are in the Portland metropolitan area. But if we can identify the Portland metropolitan, I'm just giving an example. If I identify that the Portland metropolitan area are actually located in these two metropolitan statistical areas, like MSAs, or I think it's either as a MSA level or central business statistical area level, something like this is the most disaggregate levels information that I have in the data sources. If you can identify like this city is located in the combination of these two metropolitan statistical area, then we can have something. But directly from the analysis, we cannot predict at a city level or even disaggregate. The lowest level we can predict is the central business statistical area or the metropolitan statistical area. In that, using these two data sources, it's not possible to answer your question. But what we can do is, if the information is available for a city level, then the same fusion can be applied. But we need to collect the information available for a city level. But using this, no.
Yeah.
Then we do have a couple of online questions. One's really just more of a comment, somebody kind of talking about the new versus old construction and electricity consumption. Saying maybe new construction is larger and that's part of it. And then somebody's just wondering if you could go back to the slide about the predictions and repeat how the results from the different models compare.
Sure. So The left one is shows the actual predictions. The right one shows the error compared to the observed values in 2020. Please remember, I did my analysis focusing on 2015 RECS data. In 2 or 3 months ago, 2020 RECS data was available. So using my model, I projected in the future and see how much I can improve. So look at the error rate. The first one, the red one, is whatever is going on in traditional systems, simple RECS data analysis. The second one is the fused model. The third one is also the fused model. The second one is a fused model with deterministic weight or equal weight. The third one is a fused model with probabilistic weight. The error rate, I significantly reduced the error rate across all the region. And the result is consistent across all the states too. So for instance, in the West region, just focusing on the RECS model, we are off by 100 trillion BTU in the overall West region. But using my fused model and probabilistic weight, we are dropped down to only 18 British thermal unit, trillion British thermal units. So whatever the observed value and whatever the predicted value, we are 18 BTU down. Please remember, this will further go down if till now in the 2020 RECS data, I still fuse it with 2015 NSTH data. If I fuse it with the 2022 NSTH data, that means the EV share will go up. I will have now some numbers in the EV share. I will have some number in the working from home. So that will further increase the electricity consumption. So this error will go further down. So I think that answers the questions, right?
All right, thank you all again for attending today's PSU
I think
Transportation Seminar,
New construction.
the final of the fall term. For those of you joining remotely, after the seminar ends, you'll have the opportunity to complete a brief survey about today's event. Please, it only takes a few minutes and we would really appreciate your feedback. Again, join me in thanking Tanmoy for his presentation today, and thank you all for joining us, and have a wonderful winter break.